In this lecture, we look at the power rule version of the chain rule. The chain rule is the following formula. The derivative of y with respect to x is equal to the derivative of y with respect to an intermediate variable u times the derivative of u with respect to x. We motivate this formula by noting that this rule appears reasonable since the differential du will cancel out in the numerator and denominator. This can be made precise using limits. The simple power rule for derivatives tells us that if y is x to the n, where n is some real number, then the derivative is n x to the n minus 1. So one simple version of the chain rule will extend this basic power rule for derivatives to more general functions, the functions where it's not x is raised to a power, but something else. Consider a function y equals u of x to the n, where u is some function of x. Then the chain rule says the derivative is n u to the n minus 1 times the derivative of u with respect to x. Or more succinctly, y prime is n u to the n minus 1 times u prime. The power rule version of the chain rule again says that y prime is n u to the n minus 1 u prime. So let's do an example. If, for example, y is sine of x plus cosine of x to the fifth power, notice here that we have something more complicated than x that's raised to the fifth power. Then u is this sine of x plus cosine of x, this inside part. And since we know the derivative of something to the fifth power is 5 times that thing to the fourth, and we know the derivative of this inside part, sine of x cosine x, is cosine x minus sine x, then when I take the derivative of this thing, sine x plus cosine x, to the fifth power, I will get 5 times that thing to the fourth power times the derivative of that thing. The derivative of sine x plus cosine x, again, is this cosine x minus sine x. If y is u to the fifth, then y prime is 5u to the fourth times the derivative of u. What if we don't know the function u? If I just have y as u to the fifth, where u of x might be sine x or cosine x or something else, but I really don't know what u is, then the chain rule is going to give us an answer that will have to include u prime in the answer. The derivative of y equals u to the fifth with respect to x is 5u to the fourth times the derivative of u. And this will be the best we can do if I don't know what u is. If at a later date someone says, well, u is sine x plus cosine x, then I can stick in sine x plus cosine x plus u, and the derivative of sine x plus cosine x for u prime. I can substitute for both u and u prime. We will find this notation convenient at a later time when we do implicit differentiation. Before we leave this chain rule and power rule lecture, let's explain the quotient rule in terms of the product rule, power rule, and chain rule. We learned earlier that if y is u to the fifth, then the quotient rule gives us this expression, u prime v minus uv prime all over v squared. But if we did not know this, if we did not know the quotient rule, but we knew the product rule and the power rule, then we can rewrite y in a multiplicative form. U over v is the same as u v to the minus 1. By the product rule, we will get u prime v to the minus 1 plus u times the derivative of v to the minus 1. But what's the derivative of v to the minus 1? By the power rule, the derivative of v to the minus 1 is minus v to the minus 2 times the derivative of v. So if we have a quotient u over v and we write it as uv inverse, then the product rule will give us this expression, but we know the derivative of v to the minus 1 is minus v to the minus 2v prime. We can substitute that in, replacing the derivative of v to the minus 1 here in my expression with its value, and then clean that up just a little bit. So we have u prime v to the minus 1 minus u v to the minus 2 v prime. I can write that as fractions. I can get a common denominator and get this, and there's the quotient rule. The quotient rule can be thought of as applying the chain rule to the power rule and the product rule. We'll use this in an exercise. We're going to take the derivative of x over x squared plus 1 in two ways. In one way, I'm going to use the quotient rule, and the other way, I'm going to use the chain rule applied to the product rule. Some people teach the chain rule as really the product rule. Some people teach the quotient rule as the product rule and chain rule. I don't think that's effective, but it is worth knowing that you can do it in several different ways. If I use the quotient rule to take this derivative, x over x squared plus 1, then my Numerator will be the derivative of x times x squared plus 1 minus, write down the numerator and take the derivative of the denominator, all over the denominator squared. There's my quotient rule. I can simplify the numerator a little and write it this way. So the quotient rule tells me that the derivative of x over x squared plus 1 is this expression. However, on the other hand, I can use the product rule and take the expression we had earlier and just think of it as a product, as x times x squared plus 1 to the minus 1 power. If I do that and just simply use the product rule, then the derivative of x is 1, write down the other piece, plus now write down x and take the derivative of x squared plus 1 to the minus 1. That will be, by the chain rule, minus 1 x squared plus 1 to the minus 2 times the derivative of the inside part, which is 2x. If I write that as a fraction, I get this. If I use a common denominator, I can rewrite it in this way, and there's my answer again. In the next presentation, we apply the chain rule to transcendental functions, like exponential functions or trig functions.